So let's start. Okay. So good evening, everyone. Sorry, I didn't hear you.
Yeah, you can start the session.
So good evening, everyone. Today we'll be dealing with column BBS. So basically, the column BBS, the drafting part is almost similar to that of a beam BBS. So for doing that, I'll be showing you an example of column BBS, which we have already prepared for another project. So firstly, while doing the drafting part, the first step is to analyze the foundation drawing. That is whether to determine the type of foundation provided for each and every column before doing the BBS. So since the column is a vertical structure extending from the foundation to different floors, we need to draft the entire height of the column, that is right from the foundation to the top of the building, wherever the column continues. So firstly, let us check on the structural drawing provided. So this is the most important drawing, which is the pile and foundation layout. So in this foundation layout, we get the idea of different types of columns. That is, in this, we can see that columns named C4, C2, C6 and all. That is, these are all the different types of columns used in this type of building. And next, we can see that some circles and squares and PC1 and all. These are the type of foundation used, or the foundation structure in which each columns rest. So in this figure, we can see that this red column with yellow hatch is basically the column. And this red the red rectangle with yellow hatch is basically the column. And the circle and the yellow rectangle is basically the pile cap. So here we can see that the column C4 rests on the pile cap PC1. Similarly, in this case, here the column C2 rests on the pile cap PC1. So similarly, there are different type of columns and pile caps as well. Here we can see that another type of pile cap in the shape of T, and this is PC5. Apart from pile cap, we also have footing, that is isolated and combined footing. And footings are basically represented by F1, F2, and F4. We can see here the column C1 rests over the foundation or footings F4. And here the column C1 rests on combined footing CF1. So we are also provided with a table detailing the different types of column. So here we can see that there are 8 number of columns starting from C1, C2 till C8. And this table represents the dimensions. That is, the C1 column has a dimension of 200 by 400. And the type of stirrups used, that is, this particular column contains 2 type of ties. That is similar to the stirrup in the case of beam. We have ties in the case of column. So in this particular C1 type of column, we have 2 type of stirrup ties. That is a rectangular one and a C-shaped one. And coming on to the rebar details, the main bars are 6 number of 12 mm diameter, and the ties are arranged in the special confinement zone. We'll be coming to the confinement zone in the coming sessions, and here in the confinement zone we have 8 mm die bars arranged at a distance of 100 mm center to center spacing, and in the areas, that is apart from the confinement zone, we have 8 mm ties arranged at 150 mm center to center spacing. So similarly, we have the details of each and every column. Next is the detailing of foundation or footing. That is, when we look onto this figure, we can see that there are different types of footing, that is C4, CF1, F2, and all. So this is the table which gives us an idea of the details of the foundation having footing. So here we are also provided with a typical section, that is a section BB, which passes along an isolated footing, and section AA, which passes along a combined footing. So when this is the plan view and this is the sectional view. And by looking onto this plan view, we get the idea of what A, B, X1, X2, D1 and D2 denotes in this particular table. That is, in this table, we can find that the F1 type of footing have A value of 1500, B value of 1700, X1, X2, and so on. So what this actually means is that A and B are the base dimensions of the bottommost step of the foundation. That is, if the foundation or footing have two number of steps, that is as shown in this figure, the bottommost step has the dimension of A and B respectively as shown in this figure. And below this below this step, we have a PCC layer that is 100 mm thick with a projection of 100 mm from the sides of the foundation footing steps. So this particular white colored rectangle denotes the PCC layer, and this yellow rectangle actually denotes the bottommost step of the footing. So next footing, that is the next step of footing, that is the first step, actually comes after this bottommost step at a distance of x2. That is, from this table we get the dimension of x2 as 300. That is for this type of footing, that is for F1 footing. If we deduct a value of x2, that is 300, from A and B, we can actually denote the second step, that is represented by this yellow colored rectangle. So after we find the second step, we can deduct a value of x1. X1 is actually the value of 300. That is, sorry, F1 is actually 400. So if we deduct a value of x1 further, we get the other set of rectangle, which is actually the border of pedestal column. And this pedestal column further on decreasing a value of 50 mm from the sides, we get the actual dimension of the column. Likewise, we should arrange this type of footing such as F1, F2, and F3 in the side. So here we can see that the height of the step of each of these footing is basically the bottommost step has a height of D2, and total height of bottommost step and the second step, that is a combination of first and second step, has a depth of D1. That is, D1 and D2 are also provided in the same table. So if we need to find the height of the single step, we need to actually deduct D2 from D1. Then we get the height of each and every step. Furthermore, we can also see that these are the main bars coming from the column. So the main bars coming from the column actually rest on the bottommost part of the footing. That is, it should continue along all the different steps and it should reach the bottommost part of the footing. And it actually rests on the main bars and distribution bars of the foundation. That is, it should rest uh, at a clear cover from the structure, and plus the diameter of the main bar of the footing plus the diameter of the distribution bar of the footing. And the minimum vertical leg, that is the rebar of the column which actually continues to the footing, should have a minimum vertical leg or minimum horizontal leg as shown in this figure, with a length of 300 mm. So we should bend this rebar to a distance of 300 mm as shown in this figure. So the next is the details of pile cap. And that is, when we look into this figure, we can see that there are different type of pile caps such as PC1, PC2, and all. So from this layout, we get the details of different types of pile cap. Here we can see that the rebar, here this is the plan view, and this is the plan view, and it is the sectional view. And from these we get the dimensions of the pile cap, that is 700 length, 700 width, and 600 depth. And the type of rebars and the spacing as well is determined from this figure. So this is a typical section of a column which rests over a pile cap. So here we can see that, and below the pile cap we have the pile. So here we'll be dealing with only the pile cap, and when we look onto this, we can see that the rebars of the column actually passes through the entire depth of the pile cap, and it rests along the bottommost surface of the pile cap with a distance of about cover of the pile cap plus the diameter of the main bar of the pile cap, diameter of this circular bar of the pile cap, plus half the diameter of the bars used in the column. So here also the minimum horizontal leg should be 300 mm. So these are the details or dimensions, rebars and all provided by the structural team. Next, we have to start the drafting part of doing the column BBS. So for drafting, uh, for our ease in drawing as well as to scan it using the beam properties in aadspro, we'll be drawing the column in a horizontal fashion as shown in this figure. So instead of a vertical drawing, we'll be drawing it horizontally. So starting from the drafting, we'll need to draft the column right from the foundation till the floor it continues. So here in this particular project, the total number of floors is basically 3 numbers, and these are the architectural drawing, and from these drawings we'll get the floor height of each and every column. That is, from here we can see that the level is marked, and from this level we get the floor height of each and every floor. So by analyzing the location of each and every column, we can first do this particular column, that is basically the column C4. So here we can see that the column C4 rests over pile cap PC1. So for drafting, first we need to draw the pile cap. Before the pile cap, we have a PCC layer of 100 mm thick and 100 mm projection from the pile cap. And since we are dealing with the column C4 and it rests over pile cap PC1, we need to find the detailing for PC1. That is, we need to find the depth of PC1. So moving on to the detailing of PC1, we have the depth of pile cap 1 as 600. So here we need to draw this pile cap dimension as 600. That is 600. After drawing the pile cap, we need to this gap between the ground floor level and the pile cap level is actually represented in the structural drawing itself. That is, if we look onto this figure, we can see that there's a gap between the ground level and the top face of the pile cap. So this gap is basically taken as 50 centimeter. So in drafting also we need to draw that gap, that is 50 centimeter over here. And later on we can, these vertical structures are actually beams. So, and these spans, that is from this beam to this beam, we have column floor, ground floor. And from this beam to this beam, we have first floor. So we get to know that the column C4 spans from foundation till first floor. So after drawing the entire floor height and drawing the beams and foundation as well, the next step is to draw the main bars. Before that, we'll need to provide the cover for the pile cap. If we measure this distance, we can see that the distance is actually 82 mm. From where did we get this 82 mm? So basically, since the foundation is an underground structure, the cover which we provide normally is basically 50 mm. And after this 50 mm is calculated, we need to deduct some diameter as well. That is, in this case, since it is PC1, we can see that the diameter of bars are all 12 at 150. That is 12 mm bars are used for all the rebars in pile cap. So when we look onto this figure, we can see that the rebar from the column actually is placed above the rebars of the pile cap. That is, this particular distance is 50 mm, and these horizontal bars and this circular bars is actually the rebar from the pile cap. So we need to deduct that gap as well. So the total rebar, so the total cover will be 50 plus 12 mm from the pile cap rebar plus 112 mm also. That is 2 number of bars now. So 50 plus 12 plus half the diameter of the column. That is, since it is C4, we have the main bar as 16 mm. So 16 mm bar. So 60, half of 16 is 8. So the total cover is 50 plus 12 plus 12 plus 8. So we get the value as 82. Later, the side cover is basically, if we measure, we can get a value of 56. This distance is basically, for columns, the side cover is basically 40 mm. And for 40 mm, we need to deduct the diameter of ties as well, ties and a half diameter of the main bar. So 40 plus ties is, for C4 column, we have the tie of 8 mm dia. So 40 plus 8 plus half of the diameter of the main bar plus 8. So we have a total of 56. So that's how both the base cover and the side cover happens to be 82 and 56 respectively. So after that, we need to draw the main bars. So uh, here also, similar to the case of beam and slab, the LD will be provided as per this equation, that is as per IS 456 close 26.241 2.1. We have the development length equation as 5 into sigma s by 4 2BD. It is already familiar to you in the previous classes. So this is the same equation which we use in the development length and lapping areas. So uh, if the development length is for us to provide a vertical leg as shown, that is, if the development length is not sufficient to provide a bend like this, we'll need to provide a minimum vertical leg as 300 mm, like shown this figure. Minimum leg as 300 mm. So here we need to provide a vertical leg as 300 mm dimension. That is 300 mm. So once the development length is provided, we can continue the main bars along different flow. So apart from beam and slab, in column BBS, while doing the drafting, the maximum length of rebar will be taken around 6 to 7 meter. Uh, because in the case of beam and slab, we'll be using the entire length of rebar, which is 12 mm, which is the length of rebar purchased from the market. But in column BBS, we'll be using the length of rebar with around only a maximum of 6 to 7 meter. It's basically, if we use the entire length, that is the 12 meter, there may be chance for the column to bend, or it can also be very much difficult for the workers to work with the entire length of a rebar, which is 12 mm. So we'll be cutting it to a approximate length of around 6 to 7 mm, and we'll be putting it as shown in this figure. So moreover, the rebar should be arranged in such a way that only one lapping is uh, provided in a single flow. That is, if we look on this figure, we can see that only one number of lapping is forming in this ground floor, and the next number of lapping is found in the first floor. And, and the other thing which we need to notice is that we cannot provide two number of lapping in the same direction, in the same side, in two adjacent side. That is, if the lapping in the ground floor is in the bottom side, the lapping in the first floor should be in the top side, not in the bottom side. That is, the position of the lapping should be repeatedly changing from top and bottom when we continue two different floors. And then the next step is to, once the lapping is completed, the next step is to provide the development length in the other end of the column also. That is, here also we need to provide a minimum leg of 300 mm. And the dimension for this lapping is also taken as development length LD. And once the main bars are drawn, we can label them. So for C4 column, we have 8 number of 16 mm diameter. So here we can divide the number of bars equally along top and bottom direction. That is 4 number of 16 mm in the top and 4 number of 16 mm in the bottom also. So one thing I forgot, that is, if we draw the section of the column in such a case, we need to draw the column along the shorter dimension. That is, the section should pass through the shorter dimension. That is, if the C4 column is of 200 by 400, the 200 dimension is smaller side. So the section should pass through the 200 dimension, that is the shortest span. So, okay, so we have now completed the drafting of the main bus. The next is the denoting the ties. That is, from this table, we can see that for C4 column, the ties are 8 mm diameter throughout, and the spacing varies. That is, in the confinement zone, the spacing is 100 mm, and in the remaining areas, the spacing is 150 mm. So, what is confinement zone? So, as per IS 13920-1993, we can see that if this is a vertical, this vertical member is a column, we can see that confinement zone is denoted by the notation L naught. So here we can see that the confinement zone L naught forms around the region where the beam column junction and the lapping area, here also the beam column junction, as well as the foundation area, that is the end where the foundation meets. So in all these special confinement zone, what is special is that the spacing of the ties will be lesser when compared to the remaining areas. That is, in special confinement zone, the ties will be arranged in a lesser lesser spacing than that in the remaining areas. So in this figure, we can have a special confinement zone, the lapping areas, beam column junctions, and the foundation. So when we divide this entire span into the special confinement zone, we can see that most of the areas we have special confinement zone and the remaining areas are only very few. So it is okay to provide the entire stirrups in the dimension as 100 mm spacing. Since the remaining areas, that is without confinement zone, the span is very much less, we can continuously provide the entire ties in a uniform spacing, which is 8 at 100 mm, which is that of a special confinement zone requirement. So in this figure, what L naught value is actually, that is from close 7.4.1 of IS 3920. We can have the L naught is should not be less than first priority is lateral larger lateral dimension, that is here we have 200 by 400, so the first criteria is 400 mm. The second criteria is L by 6 times the clear span, so here the clear span is 2910 by 6, that is the second criteria, and the third criteria is 450 mm. Since these values are very much less, we can provide the special confinement zone requirement for the entire span of the column. So this is an example for the column which rests in a pile cap, and the drafting method is similar for that of a column which rests in a footing as well. The only difference is that the footing gap and these that is the height of the step, width of the step and all will be obtained from another detail, that is the footing detail. So these dimension will be obtained from this table, and remaining every procedure is same for the column which rests in a footing. So that's all. And we here we also have two number of circular columns. So basically the entire procedure for circular columns is almost similar to that of a square column. Only difference is that uh, it is circular in nature. So here also the C7 column is circular, and we need to draw the column in a similar way which we did for pile cap and footing as well. So it is not much difficult. So once the drafting is completed, we can scan the drawing using aadspro. So like I also already said, in aadspro, we'll be scanning the column in a similar way which we did the scanning for BM as well. So before scanning, we need to take the copy of this column. That is, if we need if we take C4 for example, that is in this figure, we need to count the number of times C4 repeats. That is, if we count the C4 as 3 number of columns, that is, if this particular project have C4 as 3 numbers, that is 3 number of C4 columns are present in this building, we need to copy this drafted one into 3 different copies. So this is basically taken as 3 different copies in order to get a total rebar quantity of C4 column. Once 3 copies are taken, we can go to aadspro, and in aadspro we can go to beam, and in beam we can choose the properties, and in properties we can change the beam naming tag into C. In column in beam BBS we'll be naming this tag in beam BBS as B, and in the case of column we can name it as C, and remaining and after allocating the cover of bottom cover, top cover, and clear cover, we can close this window and we can press on scan drawing. And once scan drawing is pressed, we can select the 3 number of copies of C4 column and we can press enter. And now we can see that the scanning is going on, and we can wait for the scanning to get completed. Okay, now the scanning is completed. We can press the escape key, and now we can see that all the main bars, that is 4 number of 16 bars, and all are scanned. And this is basically the stirrup notation. And here in the stirrup notation, after scanning, we can see that it actually changes into 2 79 number, 8 mm, 200 mm at 100 mm spacing. So this 79 actually represents the number of stirrups, that is the number of 8 mm stirrup at 100 mm spacing, spanning from this point to this point. That is for this entire length, we have 79 number of 8 mm diameter ties. So from the scanning, we get to know the actual number of ties in this particular section from this point to this point. But apart from beam BBS where till this step, the actual process of BBS is completed. In column BBS, we need to continue few more steps too. It's basically in beam BBS, we'll only have a single number of stirrup at a particular section of beam. But in column, we can see that in C1 type of column, we have 2 number of stirrups, that is a rectangular column, a rectangular tie, and a C-shaped tie as well. That is, in a particular section itself, we have 2 number of ties. But in beam, we had only a single number of stirrups. So we need not continue the BBS. So in column BBS, if we need to find the actual quantity of ties as well, we need to continue few more steps too. Till this procedure, the entire step for main bars are completed, and now we'll move to the manual calculation of ties. So for learning the manual calculation for tie, I'll be showing another example for column BBS, which is done for another project. Here we can see that the column name is C3, and it is drafted for main bar, and stirrup is also marked. And after scanning, we can see that the main bars are scanned, and scanned numbers are seen, that is 601, 603 and all. That is after scanning. And here also we can see that the stirrups are scanned and the number is visible, that is 29 number of ties, 37 number of ties, 37 and so on. So for the entire column, we can see that the number of ties for each and every span. So in this particular, that is C3 column, we can see that this is the section. That is in C3 section, we can see that these many number of ties are present. That is 2 number of square shaped ties and 1 horizontal tie. So for doing the manual calculation for quantity of ties, we need to actually draft this entire structure. That is, first of all, if the dimension is 400 by 500, we need to draw a rectangle of dimensions 400 by 300. And from that, after offsetting a distance of cover of the column, that is 40 mm plus diameter and so on, and after offsetting the cover, we can get an inner rectangle. And in that inner rectangle, after deducting the cover, we can count the number of main bars. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 number of rebars. And these 12 number of main bars have to be actually drawn like this. That is after manually dividing the entire span into 3 different spaces, we can actually draw the rebars as shown in this figure. And after drawing the main bars, we can draw the stirrup around the main bars as shown in this figure. That is, this particular set of rectangle denotes the square shaped stirrup. This yellow one denotes the other square shaped tie, and this horizontal one denotes the inner rectangular tie. So these three are the ties that is present in the C3 type of column. So once this figure is drafted, we can actually have a copy of these ties as shown in this figure, and we can calculate the inner dimension, that is length and width of each and every stirrup. And as per our case, we have this hook, that is the point where the two end of the tie meets. We will be needing to bend it over a distance of about 75 mm. That is as shown in this figure. And by measuring the inner dimension, we get to see that the dimensions has 320 mm and 285 mm. After that, we'll need to draw another table as shown. Once we complete the scanning procedure, we can see that the last bar mark number is 606. And once the bar number is completed, that is after 606, since there are two type of stirrups, that is a single set of these two type of stirrups and a horizontal one, we need to provide additional two number of bar mark as 607 and 608. And the size is basically the diameter of the stirrup used, that is 8 mm. And here the total bars. How did we get the value 338? So for that we get to see this figure, that is the scanned copy. And the scanned copy, we need to calculate or sum the each and every number of stirrup in each and every flow. That is, we get to add the numbers like 29, 37, 37, 32, and 34. When adding all these values, that is each and every stirrup in flow, we get a total value as 169. So after adding all these stirrups, we get the value is 169. So since in a particular section, that is at a single section, we can see that this square stirrup is of two number. That is, we have two ties per set. That is, this stirrup is of two numbers per set. So we need to multiply the 169 by 2. So we get the value as 338. Then next comes the value as total length. So for that, we can check on the IS code IS 2502-1963. And in this table 8, we can see that this is the shape of the stirrup which we use in this column. That is a rectangular tie with a hook as shown. And here we can see that A denotes the greater, and that is the larger dimension, and E denotes the smaller dimension of the rectangular stirrup. So the total length is 2 times A plus E plus 24D. And when we look into this figure, we can see that when we actually drafted this stirrup, we can see that the inner dimension is 320 and 285. It is marked in this figure, that is 320 and 285, and the hook is 75. And we can have the total length as 2 into A plus E plus 2 into 75. By providing the values of A and E respectively, that is 320 and 285, we get the total value as 1360.64. And rounding this decimal into the nearest multiple of 5, we can have the value as 1365. It is actually denoted over here. And the value of A and E is also denoted in this table. And the next bar mark is 608, which is denoted for this rectangular type of ties. So this rectangular type of ties is actually repeated for only a single number per set. That is one type per set. So the total number of bars is just the summation of ties for each and every flow. That is 29 plus 37 plus 37, 32 plus 34. So we get the value as 169. And total length is similar to that of the previous case. That is total length is 2 into A plus C plus 2 into 75. We get the value as 4.72, and rounding up to the nearest multiple, we can have 1230. And after that, we can complete the value for A and E as well. That is the larger and the smaller dimension. And after completing this table, we can have another table, which is a summation of main bars and stirrups. Ties. So this table is actually the summation of quantity of main bars and ties. So the number 600 till 606 is actually from this table. That is the table which we exported from the aadspro. And these two number of rows, that is 607 and 608, is actually from this table which we have manually calculated just now. So here the size means the diameter of the bar. That is for every main bar, the diameter is 16 mm, and for the stirrup, the diameter is 8 mm. And for the total number of bars, the main bars are of six numbers. And here the total number of bars are obtained from this table as 338 and 169 respectively, which is shown here. Next comes the total length. Total length here, the total length can be obtained from this row, that is this row, and for the ties, we can have the total length value from this column. So after completing the total length, we can have weight per bar. So here the weight per bar is actually a multiplication of the total length by the unit weight of the bar. That is for 16 mm bar. The unit weight for 16 mm bar is actually 1.58 kilogram per meter. So if we multiply this length, that is 7225, and converting this mm value into meter value, that is 7.225 into 1.58, we get the value as 11.42. So on, we need to calculate the value for ties as well. That is multiplying this length value by the unit weight of 8 mm bar, that is 0.395 kilogram per meter. So here we get the total weight per bar as represented in this column. And the last column is the total weight. In total weight, we multiply the weight per bar into total bars. That is, here we have 11.42 into 6, we have 68.5. By multiplying these two columns, we get the column total weight. That is the total quantity of rebars in kilogram. So that's how we complete a BBS for column. It's a lengthy process, but it is very much similar to beam till the main bar scanning. And later on, a few steps is different since we have more than one ties in a particular column. So that's all for the topic column BBS. Thank you.
Thank you, Nirmala. Anyone have any doubt regarding the session? Then we can wind up the session. Thank you for joining.
Thank you, everyone.
അപ്പൊ ഞാൻ അമ്മ നാളെ എത്ര അങ്ങനെ ചോദിച്ചത് അമ്മക്ക് രണ്ട് മോതിരം ഉണ്ടായിരുന്നു അതെന്ത് അറിയാൻ വേണ്ടിയാണ് അപ്പൊ ചേച്ചി പെട്ടെന്ന് ചേച്ചി ഒരു മോതിരം എന്ത് ചെയ്തു അപ്പൊ ഞാൻ കേട്ട് നല്ല വെയിറ്റ് ഉള്ളത് വെയിറ്റ് അത് വെയിറ്റ് പറയും അപ്പൊ ഞാൻ വെയിറ്റ് ഉള്ള മോതിരം ഇവിടെ ഒന്നും ഉണ്ടായിരുന്നല്ലേ അമ്മയ്ക്ക് എന്ന് ഞാൻ പറഞ്ഞു അത് ചേട്ടൻ പറയുന്നത് അറിയാൻ വേണ്ടി ചോദിച്ചു അല്ലാതെ അത് നമ്മൾ നമുക്ക് അഡ്വാൻറ്റേജ് ചെയ്യണം നമ്മൾ വാങ്ങിച്ചു കൊടുത്ത പൈസ കമ്മലുണ്ട് അങ്ങനെ പറഞ്ഞപ്പോ വീണ്ടൊക്കെ പറഞ്ഞ് നമുക്ക് എല്ലാ വർഷം തോറും മാറി മാറി ഓരോരുത്തരെ വീട്ടിലായിട്ട് ക്രിസ്മസിന് അതെ